So, okay. So we want our models to be accurate. If we have a model that's able to accurately predict the performance of our hardware, that's good. That's great. That's our goal. If we had a model that only under predicts the performance of our hardware, that's not really useful in terms of building or informing our hardware experiment. Similarly, if a model over predicts the performance of your hardware, that's equally problematic. At the end of the day, we want our models to be accurate representations of actual hardware. And the goal with this data-driven scheme was to establish a scheme that's generic, device agnostic, as well as efficient to simulate in terms of large-scale neural network workloads. So now we have an idea of what a high-level system would look like. We also know how to accurately simulate these devices efficiently so that you can run these device operations in training workloads. What we do next is we actually implement and propose an algorithm for training Memristive neural networks. As I mentioned at the start, these devices have a lot of challenges. One of those challenges is that they're non-ideal, meaning these devices have defects. If you actually implement a software solution directly on a crossbar of these Memristive devices, you end up seeing gaps in their performance because of these defects. And so we try to come up with a scheme that's hardware aware, meaning the scheme should be able to work around those defects as much as possible while being device agnostic. Again, aligning with the theme of my dissertation, we want to propose solutions that are independent of the underlying device technology. We call this training paradigm robust hardware-aware ternary-weight networks. This work is currently under review in the transactions on nanoscale architectures, IEEE. Where to again think in terms of the categorical breakdown. I put a line over the first two categories here. What we do is that we propose a general methodology that's able to produce ternary weight networks. Ternary weight network is just a neural network where all possible weight values are ternary, as the name says. We have a 0 point and some symmetric point, in this case, plus minus alpha. So all of your layer weights are going to be one of 3 possible values. We also propose a quantitative device metric, and we find and report that that device metric is very accurate in predicting the performance of different networks against one another. And then we use different tools from the ML community, such as loss landscapes and optimization trajectories, and we use those to derive empirical insights into how device properties actually interact with network properties. And there's a logistic contribution in this work at the end as well, where we bundle all of our system and all of our libraries and functions together. And we bundle it into a Python package called NeuroTorch, which we plan to also open source soon. Going over actual methodology, again, this work is in collaboration with the team at ARL. We use 2 kinds of datasets for this work. The first is synthetic, meaning it comes from a compact model here based on 3 actual piece-size simulations, and the other is actually coming from experimentally fabricated devices. We take data points from the compact model. We feed them to our data-driven modeling scheme in order to generate jump table models. For the experimental case, we actually take data sets from experimental measurements conducted on actual devices. Datasets from both of these domains then get fed to our data-driven modeling scheme to again output a pair of jump table models, one for the set phase and another for the reset phase. There are 2 key parameters for the synthetic model. The first is the conductance variability or device-to-device variability. Ranges we see from 1 to 15%. The other is the gate source voltage. And these devices are actually 3 terminals. And then third terminal is fixed at some V gate source voltage. The other 2 you can then utilize in a very similar fashion as resistive ramp crossbars. And that's the idea there. So how do we actually implement this training scheme? We take use of weight quantization, which is a scheme in ML literature for training integer weight neural networks. and we bundle it with operations that are at the device level. So in this particular figure, what we're seeing here is again a very similar crossbar to before. The only difference here is that these devices have 3 terminals, as I mentioned. The third terminal is just fixed at some V-gate source value, voltage value. And then the other 2 we use for applying either input voltages or measuring output currents. The idea here is that with mixing our device modeling operations with quantization operations from weights, we're able to produce weights that are robust, hardware aware, as well as ternary. The way this happens is we go from our quantized weights to device conductances. We map those conductances to these simulated crossbars. And during the forward pass, we would take our inputs, map them to voltages, pass them to input wire, measure output currents, and then quantize those activations using wage operations. And then, of course, we repeat this operation for preceding layers. And then during training, your errors are quantized. You form your gradient, which is also quantized. And then you pass that to your jump table modeling operation to actually compute conductance updates. Once you have computed your conductance updates, you can go back to the weight domain and then let the training process continue for the remainder layers. Another thing we propose is the use of something we call hardware-aware inference. What we're doing here is that we take either networks that have been trained with hardware-aware training, the scheme that I just talked about, or that are just there to act as or serve as a baseline. And then we map it to an emulated mixed signal system with system-level defects or system-level sources of noise as well. Some of these sources are ADC and DAC quantization, and then we also include read noise and write noise. So if I were to take you through the actual encoding and mapping operation, so our hardware-aware training scheme outputs ternary weight solutions. For an example, quantized weight matrix, right? We may have a weight matrix that just has +1, zeros, and -1s. We convert them to 2 conductance matrices, and this encoding is a differential encoding, where each weight gets assigned to 2 possible devices. A +1 gets mapped to 2 devices, the first of which is in the higher conductance state, the second of which is in the lower conductance state. Similarly, a -1 is the other way around. The first device is in the lower conductance state, the other device is in the higher conductance state. For a 0, both devices have to be in the same conductance state. And you can either choose both of them to be in the higher conductance state or the lower, whichever has lower variability, if that information is known. The idea here is that with this differential realization or differential encoding scheme, we can implement negative weights very easily. Right? Because device resistances or conductances can't really take negative values themselves, they're physical quantities. And with this differential encoding, that problem gets solved. The overall idea here, the reason why we're doing this hardware-aware inference is to actually assess the effectiveness and robustness of our hardware-aware training scheme. In terms of network details, the primary results that I'll be showing in the main presentation, it's going to be a 2-layer perceptron network trained on a reduced version of MNIST. But at the end, we also conduct simulations on much larger networks on a variety of dates. Just to showcase that our approach is actually general in terms of scalable, in terms of producing solutions and training different kinds of neural network architectures. The biggest network we have is trained on Cypher10 with an AlexNet-like architecture and has a total of 12 million parameters. And at the end, we will also show how our approach, compared to counterparts in literature, produces robust hardware-aware weights to a higher degree compared to a few works in literature that are counterpart. Okay, so moving on to the results. I want to briefly talk about these 2 plots here. What we're seeing is that we take compact model data at different values of gate source voltage and variability. For this particular plot, the gate source voltage is fixed at 0.9 volts. And then we're sweeping or increasing the variability. As we increase the variability, as you can see, the shaded region in the purple curve is much higher compared to the shaded region in the black curve. And that's indicating that those devices during their set operation would have a higher degree of variability. What we do is that using these trajectories, we compute our normalized conductance difference metric, which is this equation right here. And this is again a novel contribution, which is at the device level. It's a metric for quantifying the quality of your models at the device level. You don't need to train neural networks using a particular model to compute this metric. All it's measuring is deviations between your model against some baseline. But what we do is that once we have these models, we also train using our hardware-aware training scheme, and then we compute the modeling bias metric. And this over here, MB for short, is a neural network level metric. And what we end up seeing is that our metric, normalized conductance difference, can actually, in a way, predict the relative performance of different neural networks trained against different models to a very high degree. And there's a very high positive correlation. So these bars, firstly, this is for the NCD metric, which is at the device level. The second is for the modeling bias, which is at the network level. And so in a lot of ways, this NCD metric could be used to predict the performance of your neural networks or models against one another. The good thing about it is that you can assess the relative performance of your models without running expensive neural network simulations. I briefly mentioned how we use tools from the ML community, such as loss landscapes, to study device network interactions. A loss landscape, you can think of it as being you freeze your neural network at some point in training, and then you add some perturbation to the actual weight matrices, and then you compute how that space or that landscape would look like across 2 dimensions. What's being shown here is that if I were to just summarize, we want to have flatter loss landscapes. A network that is more robust or hardware aware would be less sensitive to perturbations to its weights. And some of the findings we had, one key result was that devices with less variability tend to have flatter loss landscapes, meaning more robust solutions. And devices that are more linear also tend to have flatter loss landscapes. And so if you were to derive insights from this work in terms of devices or how your devices need to be, you want to have devices that are less variable, or you want to minimize your device-to-device variability in your crossbars. And you have to want to have devices that are more linear compared to, for example, non-linear conductance trajectories. We also examined how these optimization trajectories would look across training. And I can cover the methodology in more detail if there are any questions. But the key idea here is that we were able to find insights at an empirical level as to why device networks are more difficult to train compared to software networks where there are no non-idealities. And we found that the reason why this happens is because the actual gradient updates are a direct result of your device non-idealities. The more non-linear or non-ideal your devices are, the noisier your gradients would be. The noisier your gradients are, the more difficult it is for your network to arrive at its final local minima in a good place. And this has kind of been a known thing in literature that device networks are difficult to train. But using this methodology, we can offer some insight that the reason why that's happening is because of these noisier loss landscapes and optimization trajectories. We also take a hardware-aware trained solution and deploy it to these emulated mixed signal systems using a hardware-aware inference methodology. So again, an optical image of our actual fabricated devices. We use these to actually measure device datasets again at increasing levels of bigger gate source voltage. Right. The blue one is at the highest value here for 1.5 volts. One thing I want you to really note down here is that as you increase your gate source voltage, the dynamic range of your devices increases. It's the same device, but based on what your third terminal is set to, the dynamic range or the behavior of the device changes. The impact that has on the neural network level is as follows. As you increase the gate source voltage, you end up seeing a performance improvement at the neural network level. And this is the y-axis of actual classification accuracy. At lower values of gate source voltage, the reason why this performance drop is happening is because of the actual dynamic range limitation that I just talked about. So at lower gate source voltages, you have very limited dynamic ranges, right? And since our weights are ternary, if you were to include system level non-idealities such as read noise and write noise, you would end up having some overlaps in the actual weights if you were to read them back at the system level. If you have these overlaps between the off and on state conductances, some of your network weights may end up becoming indistinguishable from one another, and your mapping error of actual layers would end up increasing. And that has a direct result in terms of the performance of your neural network. When you have a higher degree of these distribution overlaps, your networks, despite them being trained with hardware-aware constraints, aren't really able to attain good performance. And so despite hardware-aware training, there are additional sources of noise at the system level that sort of impact the actual performance of your memristive neural network. And even in the best case here, which is this extreme point at 2.0 volts, our network is able to only attain 75% accuracy. The corresponding baseline, however, was near 85%, but there's still a 10% percentage point performance gap. Okay, so what we're essentially seeing is that despite hardware-aware training, there is some performance gap that continues to exist. If you were to compare it against a software baseline that wasn't trained with any hardware-aware constraints, the performance gap has been minimized to a significant extent, but not to a full extent, right? It's still there. And so the next problem we solve is basically this. Despite hardware-aware training, we see that this performance gap wasn't able to get eliminated fully. And then this, all of the simulation methodologies I talked about, we took information from actual hardware devices. We took actual hardware-aware constraints in the training and inference state, but the actual neural network was still being simulated in software. And so there was a lack of end-to-end hardware verification. And so we addressed both of these problems together and try to build a hardware verified solution to fully improve this performance gap. So we do this in two ways. Firstly, we propose and build and contribute to the Daffodil prototyping system. And this is a system for benchmarking memristive neural networks. It's actually a logistic contribution to the community because there's a lack of a common platform for device researchers. This platform has three components. Firstly, we have a chip with up to 20,000 devices over here. And this is where the analog array actually is. We have a digital coprocessor that in this case is actually realized through an FPGA. And then we have some PCB board for communicating efficiently between our FPGA or the host controller and the actual analog devices. And so this is an actual realization of the initial system level architecture that I talked about at the very start. And then we bring this platform up and then we introduce and propose a fault tolerance framework for fully mitigating the performance gap. And we also report at the end that this particular fault tolerance framework is actually better in terms of the overall performance gaps that you're able to minimize compared to literature counterparts. The Daffodil work was published at the International Conference on Neuromorphic Systems, and then this fault tolerance work has been very recently accepted at Nature Communications. I already talked about the problems, but the solution they're proposing, we call it layer ensemble averaging. And again, aligning with the theme of my dissertation, which is we want to propose solutions that are device agnostic and gender. And of course, at the end, we will also show how this particular approach is better compared to counterparts in literature. And this is kind of the work which brings all of these different challenges and the solutions together and tells everything together. We will utilize data-driven modeling schemes for simulation work. We will build this hardware prototyping platform to actually verify everything end-to-end in actual hardware. And then, of course, the system we're using is based on the initial system-level architecture I talked about at the very start. So what is layer ensemble averaging? So to answer that, we need to understand why these performance gaps continue to happen. The primary reason is that the VMM operations we're implementing on these crossbar arrays, it's non-ideal, meaning the outputs deviate if you were to compare them digital or ideal outputs in software. And so we design layer ensemble averaging, or LEA for short, to reduce this deviation directly. And as a result of that, we end up minimizing the performance gap. Now, the way the algorithm proceeds is you again take some software weight matrix, you map it to certain places on your crossbar, and then you encode it, of course, also in terms of device conductances, again in this differential fashion. The reason why the the reason why we map each solution redundantly, and this will become clear very shortly, is because of this redundancy. And in this case, this particular positive conductance matrix is being mapped 3 times to the crossbar. Once we do this, what we can do is average the current outputs that were being induced by individually mapped components. And then once we have these multiple outputs, we can selectively choose how to average outputs from rows that are actually good compared to others. And we have 2 modes in this layer ensemble averaging algorithm for the mapping operation. You can either do it in a greedy fashion or a random search fashion. And then for the encoding phase, again, we have 2 particular modes, where the first is just simple encoding, and the second is RME, stands for reduced mapping error. But the core idea here is you can, instead of mapping your conductance matrices a single time, you can map them redundantly to different blocks or different areas on your crossbars, and then selectively average current outputs, making sure that the outputs you're considering for the averaging process are better or less effective compared to your devices, the overall device distribution. So as I mentioned, we firstly simulate this methodology and verify whether or not it would actually work on a larger network. And then we will also talk about actual end-to-end hardware results. So we train a 2-layer perceptron network, but now it's the full MNIST dataset. It's still trained using our hardware-aware training methodology. And then we compare our LEA, or layer ensemble averaging work, which are these red bars here, to 2 counterparts in literature. The first is the mapping algorithm with fault tolerance, or MAO. The second is the committee machines algorithm. We had one particular non-ideality to our simulation framework. It's called stuck at faults. What this means is that certain devices in your crossbar may not be tunable at all. They may be too defective to a point that even if you try to write their state to a particular, let's say, on state or an off state, they end up retaining their original value. So certain devices in your actual mapping may be completely defective or stuck, either in an on state or an off state. Overall, we were able to prove that firstly, our algorithm performs better than these counterparts in literature at for a particular level of redundancy at any particular defect level. So on the x-axis here, we have the actual network's classification accuracy. And on the y-axis, we're increasing, going from bottom to top, we're increasing the defectivity of our chip, or the percentage of stuck devices, to be specific. So when there are no stuck devices in our crossbar, of course, all of our networks attain close to ideal performance because there are no defects in your devices. But as you increase this, of course, the network ends up losing performance because of non-idealities and because of deviations in the mapping error. But what I want you to understand here is that for a fixed stuck percentage, let's say 20%, layer ensemble averaging induces a higher degree of fault tolerance, which is evident from the higher accuracies, right, compared to the other counterparts. Especially at 40%, you can see that this difference becomes even more evident. And again, the reason why this is happening is because layer ensemble averaging is able to reduce these mapping errors to a higher degree compared to these 2 counterparts in literature. Another key result here is that the performance gap problem that I initially talked about and I've been talking about, that continues to exist. Using this simulation verification work, we were able to see that if you have 10% devices or even 20% defective devices, stuck devices, layer ensemble averaging can actually induce fault tolerance to a degree that's very close to your ideal baseline. And so given enough redundant devices, you can finally resolve that performance gap fully. We take this methodology, we implement it on an actual Daffodil prototyping platform. Instead of using the MNIST dataset, we now use a variant of this yin-yang dataset. The reason why we don't use MNIST is because the hardware prototyping platform has a limited number of devices, and it wouldn't be feasible to actually try and implement an MNIST scale network, and then also have some degree of redundancy for verifying the effectiveness of your ensemble averaging. And so this is a classification problem. You're given input data points, and the task is to classify which part of the yin-yang symbol each point corresponds to. We take a single variant and we convert it to a continual learning problem in order to make it more difficult, and in order to make the requirement on the fault tolerance phase of Lie ensemble averaging to a higher degree. We take this network, we train it on instances from task 1 for a certain number of epochs. We stop training, let's say at epoch 100, we stop training on instances from task 1, and then the network starts seeing instances from task 2. While it continues to learn task 2, it should retain performance on task 1. And that's what makes this problem and this neural network a lot more difficult than just a single classification problem for task 1. Now, your neural network has to be more robust to device level non-idealities in order to see any performance improvements and any performance, any reduction in performance gaps really has to come from the actual algorithm itself. And so towards the right here, I have on the x-axis, we have redundancy levels. I want you to focus on these 4 data points at alpha equals 4. What this is showing is that for the given network that we've already trained, if you were to deploy it on defective crossbars on the actual hardware prototyping platform, increasing the level of redundancy or increasing the number of rows that you considered for averaging directly corresponds to increase in increments in your network's performance. The baseline here is around 72%, and at the highest level of redundancy, we're able to finally see that we get performance that's within 1% of the actual baseline. So no performance gap if you have at least a redundancy level of 4. At the bottom plot, the only difference is that we're now using random mapping. And so the primary difference here is that your random mapping scheme only samples a subset of possible locations on your chip. And so it's much faster than the greedy scheme, but then of course the trade-off is that your distributions wouldn't be as nice, or as you may end up getting higher performance drops. You would ideally want to increase the number of sampling iterations that you use for the random mapping phase, but it's a trade-off. It depends on your use case. Overall, here we've been able to show that higher redundancy benefits all configurations. You also see how the greedy mapping phase yields tighter distributions compared to the random mapping phase. And overall, their ensemble averaging is very effective in reducing the performance gap at inference time. So you have a solution that you're deploying to your crossbar. The solution may have been trained already with hardware-aware constraints, but you want to make sure that even after deployment, your network attains or retains performance that's close to your actual software. If you have redundant devices, this is a very good solution where we're able to demonstrate and show that our networks can attain near software performance, both on a simulation problem or a simulated problem, as well as an actual problem implemented on actual hardware. One key point that I want to highlight here before I move on is that this is the first hardware demonstration of any fault tolerance framework for Memristive Neural Networks. All previous works have been either purely based on simulation or a mix of hardware and simulation. This is the first demonstration that's happening end-to-end on the Daffodil prototyping platform. Okay, so moving on, the last part of my dissertation actually focuses on much larger networks. In particular, it focuses on LLMs. The key problem here is that every network we've trained so far, the largest network had a few million parameters, the AlexNet network, whereas modern LLMs are approaching the trillion parameter range. So there's a huge gap there still. The reason why investigating such networks is still important is because power and energy concerns would be much more evident and much more, we need to be considerate of those or at such scales in order for them to be effective. And the question we answer next is, would a memristive accelerator for LLMs be plausible? This work was done at Western Digital during an internship funded by NSF. We can't really simulate these networks, or we can't really implement these networks on our prototyping platform. Again, because of the sheer difference in scale, LLM layers are extremely huge, and we just have 20,000 devices in our prototyping platform. So what we do instead is we utilize all of our insights from our hardware-aware training and simulation work in order to build a noise model or a device noise model for very large-scale memristive networks, in particular LLMs. And for this work, we'll be using, again, binary MRAM devices in order to, again, ensure the solutions we propose for simulating are firstly device agnostic and secondly gender. There's a logistic contribution here in terms of the actual framework we built. There's also a scientific contribution, which is to actually study and derive critical specifications of actual devices that would be needed for a memristive LLM accelerator to be possible. So there are two key steps in the device noise model. First is that we inject noise sources that would be present to pre-trained transformers. And for this, we utilize the Hugging Face library for transformers. This really enables conducting these simulations very efficient because you can take pre-trained models from the Hugging Face hub, inject non-idealities on top of them, and then really simulate them end-to-end in a very efficient fashion. We're also able to integrate with the language model evaluation library. And this is a library that really makes it easy to benchmark your networks. Once you have LLMs that are pre-trained, that have been injected with noise sources, you can provide different benchmarks, different common benchmarks for natural language processing. And you can really simulate this end-to-end, making sure that your weights are including device level constraints. So how it looks in terms of the overall flow, we still have a network layer in software, right? We'll still apply inputs in terms of voltages, and we'll still gather outputs in terms of currents. The key difference here is that now we'll be splitting or including the modeling of this array partitioning operation, and I'll explain why this is important for this particular noise model. But we do these vector matrix multiplication operations across multiple arrays, and we simulate how the operation would happen if you had arrays that were smaller than your neural network layer. And then all of this gathering operations are presumed to be done digitally. The device noise model overall supports a total of 5 noise sources, 3 of which we've kind of already seen. We have stuck-at faults, ADC and DAC quantization, the inputs and outputs. The 2 sources I do want to explain here and briefly cover are firstly conductance variability, and then this array partitioning that I mentioned. Okay. So we include conductance variability in our device noise model. What conductance variability means is that all of your devices tuned to a particular state may have some distributional spread, right? So at 0% on-state variability, you would have all of your devices tuned to, for example, 100 microsiemens actually take that exact value, right? And then similarly for the off-state, there is a relation between the noise of your on-state devices against your off-state devices governed by these equations. And the noise itself is multiplicative. And what that means is higher your noise level, the more your spread would be in terms of the overall distribution your devices end up in. And you could imagine a scenario where if this, this parameter is very high, then your distributions may end up overlapping. And that would again create problems in terms of network performance. But this is an important consideration, especially for modeling MRAM or binary devices accurately. These devices typically have multiplicative noise that you want to model in order for your model to be accurate. Now, moving on in terms of array partitioning, The reason why we now consider partitioning these arrays is because LLM layers are significantly large, and it would be unrealistic to assume that you could just go ahead and build an equivalent crossbar array that would have enough units to perform the entire VMM operation on one block. And so in the device noise model, we include the capability of modeling or partitioning your arrays. The other thing we include here are IR drops. If you have enough, if you have crossbars that are very large, one operation that ends up dropping your network performance are these IR drops. And so your crossbar devices actually have resistances both at the rows, at connecting row points, as well as connecting column points. And these resistances cause IR drops, meaning that if you were to apply, let's say, just for the sake of example, 0.3 volts to all lines, the near device or G11 would end up seeing a value very close to that intended voltage, but the far device would end up seeing a significantly lower voltage value. And again, this would manifest in terms of firstly mapping errors or VMM errors in the VMM operation, and then that would translate to errors and then a drop in performance. And so this is a plot on how these IR drops are modeled in literature. And then over here to the right, we have a representation of how these planes could be simulated across different crossbar sizes, as well as different wire resistances. And so at a fixed wire resistance, you could either sweep the conductance of your on-state devices. That's what you're seeing here. And now you could fix your on-state conductance and then sweep wire resistances. And the quantity that's being plotted here is the effective change in conductance. So the ideal conductance divided by the effective conductance you're able to read or access back. Over here is just a phenomenon, is just the array partitioning noise source that I talked about. We're fixing the actual LLM layer to be deployed. And that layer in this particular example has 3K by 3K dimensions. If we had a crossbar of the same size, our IR drops would be too bad to the point that the effective conductance drop somewhere around the midpoint of your array would end up approaching infinity. And this is very non-ideal. What you can do is fix all parameters, but then make your crossbars smaller in this device noise model. And what that ends up doing is now your VMM operations would end up getting split across multiple arrays, but your IR drops would end up impacting your performance much less. So if you just compare these labels on the y-axis, you can see going from all the way from infinity to 12 all the way down to less than 2. And your IR drops, basically what's happening is that they impact your network's performance less and less. The trade-off, of course, being that now you'll have to do these array partitioning operations to a higher degree. Quickly going over the actual LLMs and benchmarks that I'll be talking about. We use two primary language models. The first is called the tri-LM model, which still has ternary weights. But then at the end, we also have results showing a 5P model by Microsoft, which has 14.16 weights. And we show how you could still use binary devices to implement such a network for an effective Memristive LLM accelerator. And then we conduct or evaluate the performance of these language models under various noise sources through the device noise model. And we evaluate the performance for a bunch of benchmarks for natural language processing, ranging through a bunch of different categories, common sense reasoning, language understanding, so on. There are a lot of datasets here. The ones that are grayed out are LLMs, don't really attain good performance on them, even in an ideal scenario. And so I won't be talking about those. But all of the other ones are going to be included in the results I show. And over here to the right, I have a representation of what one of these datasets looks like. It's the physical interaction question answering dataset, where your language model is presented with a question requiring some understanding of physical interactions, and the network has to choose either option A or B. And so in a way, this is just a binary classification problem, right? Just in natural language. And even in a worst case scenario, if your model were just guessing randomly, would still attain close to 50% performance, just because there are two options, right? Okay, so moving on to the actual results. What we do is we take the tri-LM model, we add the noise sources from the device noise model, and then we sweep those noise sources, and then we add all of those one on top of the other, and try and understand and derive specifications at the device level that would be needed to attain or make this accelerator plausible, right? So over here, this first plot, what we're doing is sweeping the on-state conductance variability on the x-axis. There's this green region here that I've highlighted, and then this red region here that I've highlighted. This green region corresponds to the area or the conductance variability that you could effectively tolerate. What that means is that even if you had 15% variability in your on state, your devices or your LLM accelerator would still be able to attain a performance that's very close to the ideal baseline. But if you were to increase that conductance variability, and if you were to just continue pushing it to beyond this red region, you would end up seeing that the performance for any particular benchmark is as good as random guessing. For this, again, this purple curve corresponds to the Pika dataset that I talked about. And in this red region, you can clearly see how it ends up becoming just a random classifier, right? And so we want to stay in this green region. We want our devices to, in the worst case, have 15% conductance variability. So the next thing we do is that we, at a fixed conductance variability, simulate ADC and DAC quantization at increasing levels of precision, and that's the second plot here. The green region here corresponds to again the area where our language models would be able to attain good performance. The key idea here was that at a fixed conductance variability, we also wanted to develop an idea of the precision our ADCs or DACs would need to be for this system to actually work properly. And so the result here is that we need at least 12-bit ADCs and DACs for this to work efficiently. And then we can also do this at increasing levels of conductance variability, and then checking a similar plot for the ADC and DAC precision. And we end up seeing that regardless of where you are in this green region, this 12-bit number still holds. Okay, so next I want to quickly present the array partitioning and the IR drops I talked about. So this is just now for the Pika dataset, this plot to the left. What we're doing is these bar plots are grouped by increasing wire resistances. And then within each group, we have, going from left to right, larger crossbars. What we're seeing is that if you have wire resistances that are even just 3 ohms, and this is a small number, but there is a point if you have large crossbars, for example, this darkest bar here, 1536 by 1536 crossbars, can't really attain any good performance at all. However, if you were to make your crossbars smaller, you do gain some performance improvements back, right? And this again holds true for all cases. Of course, when there's no wire resistance, there's no performance drop at all. And so in a way, we can mitigate the impact of IR drops using this. We can mitigate the impact by making our subarrays smaller, or the partitioning to smaller subarrays. However, we would ideally want to have these larger subarrays, right? Because larger subarrays directly correspond to faster computations. And so is there a way, or can we come up with a way to actually mitigate this problem of IR drops without necessarily resorting to smaller subarrays? And the answer is yes. What we can do is view this as a device engineering problem. We fix the wire resistance, we fix our crossbar array size, and then what we're doing is that we're engineering our devices to be more resistant or less conductive. So going from right to left now, what we're seeing is at a fixed wire resistance and crossbar array size, in the worst case scenario, your network's performance is too bad, right? We want to be near the baseline. But if you make your devices more conducting, you can actually gain the performance back. And so this is the key result here, is that you can actually build an LLM system or an LLM accelerator based on Memristive devices using these, and you can really study them at different levels and specify different noise sources very effectively. And at the end, we can also even bundle all of these noise sources on top of one another and then study what specifications your devices and system would need to have in order to get, in order to stay in that green region. And so in order to answer, just answering the initial question I posed, would such an accelerator for LLMs be plausible? The answer is yes. You would want to have devices that are more resistant in order to enable larger like in order to realize larger arrays, and possibly even low power write operations. And the noise model that we've built, it can actually be fed actual experimental data in order to make it more accurate. Okay, so summarizing everything, we started off by proposing a high-level system architecture. We proposed several algorithmic optimizations. We studied gradient decomposition and recomposition methods. We then moved on to actually simulating these devices at an accurate at an accurate level, such that those simulations would still be efficient as well as accurate. We proposed a hardware-aware training scheme, right, that produces robust ternary weight network solutions. We also proposed several quantitative metrics that could be used to assess the quality of both your models as well as corresponding neural networks. We also showed how you could use different tools from ML literature to actually study device network interactions in order to develop a better understanding of what's happening between the devices, different device qualities or properties, and your neural network performance. And then over here at the end, we also proposed the hardware-aware inference scheme, taking different solutions and then deploying it to an emulated system in order to study whether your hardware approach is actually efficient in producing solutions that are robust. And then a logistic contribution here was the NeuroTorch framework, which kind of bundles everything that we've seen throughout my dissertation together. We then went on to actually talk about Daffodil, which is a hardware prototyping platform for the Memristive research community. This again is a logistic contribution. But then using this framework, we took and verified all the different parts, and then we verified and proposed the layer ensemble averaging algorithm, which is a fault tolerance framework that you could implement on top of hardware-aware training and inference, right, in order to finally mitigate the performance gap problem. At the end, we zoomed out to larger networks such as modern LLMs. We developed a noise model that's very accurate in predicting the performance of different, that's very accurate in depicting how your Memristive neural network accelerator for LLMs would be. This was again a logistic contribution, but then using this, we established a methodology which you could utilize to study different device and system level specifications. Overall, all of the things I talked about, different parts of my dissertation have been disseminated at different venues. We have a total of 6 papers, one of which is under review, as well as a recent patent and several conference presentations. I want to conclude by firstly acknowledging my advisor, Professor Gina Adam, all of my committee members for their time, and for really helping me shape my dissertation into what it is. Everyone at the Adam Lab for being wonderful colleagues. We have some people online as well, I know. And then, of course, the agencies for funding this work. And with that, I open the floor to questions, comments, feedback, and suggestions. Thank you.
Any questions from either the committee or from the audience?
Yes.
You mentioned in the first part about MTV being better than prediction. Can you just reiterate what they are?
Sure. Okay, so we have a question from Samir, who is present here in person. And the question is, why is the MTD metric better at predicting the quality or the performance of these ternary weight networks, right? Okay, so the reason why it's actually better is because in these ternary weight networks, we're only ever utilizing these two conductance states that are at these extreme ends. So either the off-state conductance or the on-state conductance. And so it just happens to be the case that at the levels of variability that we're investigating, all that matters for the actual neural network performance is the average conductance trajectories or these dynamic metrics. And of course, the normalized conductance difference matrix directly captures this. And so that's able to better explain neural network performance metrics.
On the topic of redundancy in the networks, so at one point, I think you said there was something about like 4 times redundancy was very good.
Yeah.
I forget exactly what that was in reference to, but did you consider the comparison in performance? Because you have redundancy, theoretically, you could get a bigger network with less redundancy, right? Running with the same number of parameters.
Yeah. So for this particular network, the network actually itself is quite small, as you can see, right? It doesn't have parameters that are in the thousands of lines. It's only a few hundred parameters actually, or a few thousand. That is a trade-off you could study and you could implement. However, the goal of this layer ensemble averaging is that you also need to take into account the actual defect level of your devices. And so at a specified number of defects or number of stuck percentage, a number of devices in your chip that are stuck, right? You want to study redundancy for that particular case. And this hardware, of course, this is based on actual hardware results. And so we didn't really have direct control of how defective our devices are, right? And so for this particular case, what we ended up doing is investigating or sweeping the levels of redundancy that would induce fault tolerance to an extent where our hardware network could attain a performance matching the ideal software base. And it happens to be the case, again, that for this network, that number ends up being around 4. You could, in theory, study this at even a higher level of redundancy, but then the trade-off is the more redundant you map, the lower your computations are. And so ideally, you want to establish a balance between those two parameters. Yes.
In slide 11.
Slide 11.
Yeah, almost there. That's 12. There you go. Perfect. So we talked about 2 sets of ternary weight networks. One where you were trying to do this for large models, and so you weren't using these jump tables. But this one, you're still using the jump tables, and I'm having a hard time understanding what is being modeled here. Are you modeling that if you were trying to train a ternary network in situ by applying pulses and in situ realizing what the ternary weights would be at the end? I see the value in that, but then if you are going through all of this effort to show how that is, what's going to be missing in something where you just do direct transfer of ternary models that don't take into account this? Because it seems like if you're going through all this work to do this pulse and these jump tables and so forth for this, if that's really necessary, does that mean that the work was done at Western Digital is somehow at risk of missing something?
So 2 answers to that question. I'll answer the first part. We're not simulating how an actual in situ hardware memristive crossbar that's modeling ternary weights train. The thing we're modeling here is the goal is that we want to have ternary weight networks that are robust to general device non-idealities. The core operation these jump tables are modeling is that during training, the actual weight updates are no longer directly proportional to your original gradient. They're proportional or related through this jump table model. And so there is no non-idealities at the network level that are going to happen during those gradient updates. And so in a way, if you were to think of this as kind of a regularization on your training, you're modeling or device non-idealities through these jump tables in order to make your networks more robust. Once you have those robust networks, you can map them to either an emulated system, which we do in this section, as well as the work at Western Digital, right? Where we have an accurate model of at inference time. But what we show here is that those 2 approaches are also separate in a way. You can train hardware-aware networks, or you can take pre-trained networks that have not been trained with any hardware-aware constraint, and you can still map them to an LLM accelerator or an accelerator that's mapping based on the differential encoding scheme. And so in the particular LLM results that I showed, there was no redundancy as far as being used plans. And so in a lot of ways, what's happening here is that for these smaller networks, so if I go back to this slide, the network we were training here was again a network for classifying the reduced MNIST, right? So it's a much smaller network compared to an LLM, right? And because of its scale, differences in hardware-aware training become much more evident. Whereas if you have networks that are at the scale of layers with 3K by 3K bits, just because of that higher level of dimensionality, your networks are fault tolerant to a much higher degree without even any redundancy. And so all of those are different ways to look at the same problem. And going back to your initial question, the reason why we have these jump tables here instead of just quantization operations, because you could swap out all of these device modeling operations and still get a ternary weight network, right? By adding these jump table models, the solutions we get are more robust to perturbations in the weights. And that's kind of the summary of
Perturbations because they've
been trained with non-idealities in mind. Constantly your gradient gets shifted to other possible directions because these pulses, like the gradient gets converted to pulses. You look up pulses against in the conductance domain using these jump tables. But then those updates may have some non-linearity or non-ideality or some variability.
These are non-idealities that come in because of the programming process?
Yes.
I see.
Not necessarily. So sorry. So if I go to my conductance trajectory slide, okay, so you can clearly see one non-ideality over here is the overall variability, right? Where if you have a higher degree of variability in your devices in the crossbar, you would have a slightly different response compared to if you had a lower degree of variability. And so this itself is not a result of the actual programming scheme. But there may be some other sources of defects or some other noise sources that are a result of these that are a result of this scheme. But over here, for our jump table modeling scheme, it's a completely it's a completely data agnostic scheme, meaning it doesn't care where that data was coming from. It doesn't care about what individual sources contributed to that data set. Once you have that conductance data set, conductance versus change in conductance, you can feed it to the jump table model and then get average statistics of what your devices would look like if you were to apply voltage pulses given some initial conductance.
But then I'm still trying to figure out what exactly what is the weakest link in these small arrays? Like how does this, what exactly is it more robust against?
Sure, it's more robust against a network that was trained without any device constraints or device operation.
But okay, but what is specific about that network?
I'm sorry, I don't think I understand that part.
Yeah, maybe.
I understand this work and how it relates to everything. I don't think I understood your question fully. Could you repeat that last part?
Well, I mean, we're talking about device variabilities here, and you mentioned there's many characteristics here, nonlinearity. Are you saying that in general, this method gives you more robustness against all of those non-idealities?
Yes, and in this particular case, we've shown it for two parameters, device-to-device variability, as well as the gate source voltage, which directly relates to devices' linearity or non-linearity.
Okay.
Yeah. But for the experimental part, those devices had other kinds of non-idealities as well, right? Where there is also a difference in your dynamic range by a lot compared to the synthetic device. And so you can take this data, you can take compact model data that has a lesser degree of variability or a higher degree of variability. And in general, what we've shown is that if you try and compute a baseline for your hardware-aware network, what would that baseline look like? It wouldn't have any device modeling operations, right? And so if you were to compute the performance and the loss landscapes, the networks we trained with our hardware-aware approach have flatter landscapes. And so they're less sensitive to perturbations to the actual ternary weights.
Okay.
Any questions from the audience? Online? Are there any questions online?
No, we don't have any online questions.
Then maybe we can move to the committee discussion. So all the audience will see.
Okay, so we do have some light snacks in the pantry area. Be sure to grab a light snack before you leave.
So I have one quick. So I think since we are in the committee deliberation stage now, probably we can stop the recording of this video.
Okay, stop the recording. Thank you everyone online for joining. We will now be sharing